Hello viewers, presenting a new topic, recurrent neural networks, RNNs. Let's start the topic. Recurrent neural networks, RNNs, are a type of neural network particularly suited for sequential data processing. Sequential data, RNNs, are well suited for handling sequential data because they have a built-in mechanism to capture dependencies over time. This makes them effective for tasks where the order of elements in the input significant, such as time series forecasting, natural language processing, speech recognition, and video analysis. In these tasks, the context of each element depends on the preceding elements, and RNNs are capable of capturing these temporal dependencies through their recurrent connections. Feedback loop. This feedback loop is a crucial aspect of recurrent neural networks, RNNs. It allows information to flow through the network over multiple time steps by feeding the output from one step back into the network as input for the next step. This mechanism enables RNNs to maintain a form of memory or context across the sequence, making them well suited for tasks involving sequential data where past information influences future predictions. Variable input length. One of the advantages of RNNs is their ability to handle inputs of variable length. Unlike traditional feed-forward neural networks, which require fixed size inputs, RNNs can process sequences of varying lengths. This flexibility makes them suitable for tasks where the length of the input data may vary, such as processing sentences of different lengths in natural language processing or analyzing time series data with varying numbers of observations. RNNs achieve this by unrolling the network for each time step of the input sequence, allowing them to adapt to sequences of different lengths dynamically. Shared weights. In recurrent neural networks, RNNs, the same set of weights is shared across all time steps of the sequence. This means that the parameters of the network, that is, weights and biases, are reused for each step of the input sequence. By sharing weights, RNNs can learn to capture temporal dependencies and patterns across time, allowing them to model sequences effectively. This parameters sharing scheme reduces the number of parameters in the network compared to having separate weights for each time step, which can help with training efficiency and generalization to new sequences. Vanishing gradient problem. The vanishing gradient problem is a significant challenge in training recurrent neural networks. It occurs when gradients become increasingly small as they are back-propagated through time during training. This issue particularly affects RNNs because of their deep sequential nature, where gradients must be propagated through many time steps. When gradients diminish exponentially, it becomes difficult for the network to learn long-range dependencies, as information from earlier time steps may have little impact on the final prediction. As a result, RNNs may struggle to capture relationships between distant elements in a sequence, limiting their ability to model complex temporal patterns. Several techniques have been developed to address the vanishing gradient problem in RNNs, including using alternative architectures like long short-term memory (LSTM) networks and gated recurrent unit (GRU) networks, which incorporate mechanisms to better preserve and update information over time. Additionally, gradient clipping and careful initialization of weights can help mitigate the impact of vanishing gradients during training. Long short-term memory. Long short-term memory LSTM networks are a type of recurrent neural networks architecture designed to address the vanishing gradient problem and capture long-range dependencies more effectively. Long short-term memory networks achieve this by introducing memory cells and gating mechanisms that regulate the flow of information through the network. Each LSTM unit contains a memory cell that can maintain information over long periods of time, allowing the network to retain important information over many time steps. The key components of an long short-term memory unit include memory cell. The memory cell is responsible for storing information over time. It can selectively remember or forget information based on the input and current state. Forget gate. This gate controls the flow of information from the previous cell state by determining which information to discard and which to keep. Input gate. The input gate regulates the flow of new information into the memory cell. It determines which values from the input and current state should be. Output gate. The output gate controls the flow of information from the memory cell to the output. It decides which information to output based on the current input and state. By incorporating these gating mechanisms, LSTM networks can effectively handle long sequences and capture dependencies over time, making them well suited for tasks such as language modeling, speech recognition, and time series prediction. Gated recurrent unit, GRU. The gated recurrent unit is another variant of recurrent neural networks designed to address the limitations of traditional RNNs, particularly the vanishing gradient problem, while being computationally more efficient than long short-term memory networks. The key feature of GRU is its simplified architecture compared to LSTM, achieved by combining the forget and input gates into a single update gate. This reduces the number of parameters and computations required, making GRUs faster to train and less prone to overfitting, especially when dealing with smaller datasets. The main components of a GRU unit include update gate. The update gate in a GRU determines how much of the past information to retain and how much new information to incorporate. It combines aspects of the forget and input gates in LSTM, controlling the flow of information into the current state. Reset gate. Some GRU implementations also include a reset gate, which controls the extent to which the previous state affects the current state. However, not all GRU variants include a reset gate. By using fewer parameters and a simplified architecture, GRUs offer a good balance between performance and efficiency, making them popular choices for various sequential data tasks such as natural language processing, speech recognition, and time series analysis. Directional RNNs. Bidirectional recurrent neural networks are a type of RNN architecture that process input sequences in both forward and backward directions. By doing so, they capture information from both past and future context, enabling them to better understanding the relationships and dependencies within the sequence. In a bidirectional RNN, the input sequence is processed in two passes, one in the forward direction and one in the backward direction. Each pass generates a separate set of hidden states which are then combined to form the final representation for each time step. This combined representation incorporates information from both past and future contexts, providing a more comprehensive understanding of the sequence. Bidirectional RNNs are particularly useful for tasks where context from both directions is important, such as natural language processing tasks like part of speech tagging, named entity recognition, and sentiment analysis. By leveraging information from both past and future contexts, bidirectional RNNs can improve the accuracy and performance of these tasks compared to traditional unidirectional RNNs applications. Recurrent neural networks have found widespread applications across various domains due to their ability to effectively model sequential data. Language modeling. RNNs are commonly used for language modeling tasks where they predict the next word in a sequence of words. This is useful for applications like autocomplete suggestions, speech recognition, and machine translation. RNNs, particularly sequence-to-sequence models, have revolutionized machine translation by enabling the translation of text from one language to another. They can handle variable length, input and output sequences, making them suitable for translating sentences and documents. Speech recognition. RNNs are used extensively in speech recognition systems to convert spoken language into text. They can process audio data over time and generate transcripts to spoken words, enabling applications like virtual assistants, voice control devices, and speech-to-text software. Sentiment analysis. RNNs are employed in sentiment analysis tasks to classify the sentiment or emotion expressed in text data. They can analyze sequences of words and infer whether the sentiment of a piece of text is positive, negative, or neutral, which is valuable for applications like social media monitoring, customer feedback analysis, and opinion mining. Time series prediction. RNNs are effective for time series prediction tasks where they analyze sequential data over time and make predictions about future values. They are used in applications such as financial forecasting, weather prediction, stock market analysis, and traffic forecasting. These are just a few examples of the many applications of RNNs. Their versatility in handling sequential data makes them valuable tools across a wide range of fields, including natural language processing, audio processing, finance, healthcare, and more. Training. Training recurrent neural networks typically involves a process known as backpropagation through the BPTT. BPTT is an extension of the standard backpropagation algorithm used to train feed-forward neural networks, adapted to handle the sequential nature of RNNs. Unfolding the network. The RNN is unfolded over time, creating a series of connected copies of the network corresponding to each time step in the input sequence. Error calculation. The error between the predicted output and the target output is calculated using a loss function such as mean squared error (MSE) for regression tasks or cross entropy loss for classification tasks. Backpropagation. Gradient of the loss function with respect to the parameters of the network weights and biases are computed using the chain rule. This involves propagating the error gradients backward through time from the final time step to the initial time step. By unfolding the network over time and applying backpropagation, BPTT allows RNNs to learn from sequential data by adjusting their parameters to minimize the error between predicted and target outputs. However, BPTT can suffer from the vanishing gradient problem, particularly in deep or long duration sequences, which can make training challenging. Techniques like gradient clipping using alternative architectures such as LSTMs or GRUs and careful initialization of weights can help mitigate this issue. Overfitting. Overfitting is a common problem in training recurrent neural networks, particularly when dealing with long sequences or limited training data. Overfitting occurs when the model learns to memorize the training data instead of generalizing well to unseen data. Dropout. Dropout is a regularization technique commonly used to prevent overfitting in neural networks, including RNNs. During training, dropout randomly disables a fraction of the neurons, that is, sets their outputs to zero in the network, effectively introducing noise and forcing the network to learn more robust representations. Regularization. L1 and L2 regularization methods penalize large weights in the network to prevent overfitting. These regularization techniques add a regularization term to the loss function, encouraging the model to learn simpler patterns and avoid over-reliance on individual parameters. Early stopping. Early stopping involves monitoring the model's performance on a separate validation dataset during training and stopping the training process when the validation error starts to increase, indicating that the model is beginning to overfit. Model architecture. Using simpler model architectures or reducing the number of parameters in the network can help prevent overfitting, especially when dealing with limited training data. By applying these techniques, practitioners can train more robust and generalizable RNN models that perform well on unseen data, even in the presence of limited training samples or long sequences. Teacher forcing. Teacher forcing is a training technique commonly used in recurrent neural networks, RNNs, particularly in sequence-to-sequence learning tasks such as machine translation or sequence generation. In teacher forcing, during training, the true output sequence or a portion of it is provided as input to the network at each time step. Instead of using the model's predictions from the previous time step, this means that the model receives ground truth information during training, allowing it to learn from the correct sequence of outputs. Stability. Providing ground truth information during training can help stabilize the training process, especially in the early stages of learning when the model's predictions may be inaccurate. Reduced exposure bias. RNNs are prone to exposure bias, where they are trained to predict the next token based solely on the previous ground truth token. Teacher forcing mitigates this bias by occasionally providing the model with its own predictions during training. Faster convergence. By providing more accurate and informative input during training, teacher forcing can help the model converge faster to a solution. However, it's worth noting that during inference, that is, when the model is generating sequences without access to ground truth, teacher forcing is not used. Instead, the model relies solely on its own predictions, which may lead to differences in performance compared to training. Techniques like scheduled sampling can be used during inference to bridge the gap between training and inference. Input embeddings. Input embeddings are a fundamental component of many RNN-based models, particularly in tasks involving text or categorical data. When dealing with discrete inputs such as words in natural language processing tasks or categorical variables in various applications, RNNs typically use input embeddings to convert these discrete inputs into continuous vector representations. This process involves mapping each discrete input to a dense low-dimensional vector embedding in a continuous vector space. Dimensionality reduction. They reduce the dimensionality of the input space by representing each discrete input as a fixed length vector, making it easier for the RNN to process and learn from the data. Semantic representation. Input embeddings capture semantic relationships between inputs by placing similar inputs closer together in the embedding space. For example, words with similar meanings tend to have similar embeddings, allowing the model to generalize better to unseen words or categories. Learnable representations. Input embeddings are learned parameters of the model and are updated during training using backpropagation. This allows the model to adapt the embeddings to the specific task and data, learning meaningful representations directly from the input data. Efficient computation. Using input embeddings reduces the computational complexity of processing discrete inputs as the model operates on continuous vectors rather than large, sparse, one-hot encoded representations. Overall, input embeddings play a crucial role in enabling RNNs to effectively process and learn from discrete input data in various applications, including natural language processing, recommender systems, and sequence classification tasks.